So there was a question on your homework, and oh no, that's not what I want to do. I just wanted this to go away. Okay, about is there a positive, negative, or zero correlation between the number of fire hydrants in a city and the number of dogs? And so is there, yes or no?
Positive.
Yes. Yes. And is it positive or negative? Positive. And that's because, okay, as number of fire hydrants, if you plotted like number of fire hydrants versus number of dogs, they tend to go up together. So does a city get more fire hydrants because there's more dogs and dogs in places to pee? Probably not, right? So do fire hydrants cause more dogs or dogs cause more fire hydrants?
Dogs.
No, right? That's crazy. That's crazy talk. So you have to be very careful to not confuse correlation, which means that that variables do something at the same time. They either march up together or march down together, versus thing one causes thing two to happen. Does that idea make sense? So that's the whole correlation does not mean causation. And like for a long time, cigarette companies use this to say that smoking didn't cause lung cancer. Like, well, smoking is correlated with lung cancer, but it doesn't, you can't say it causes it, because they didn't do a random study and say, okay, well, this half of the group of people is going to smoke and we're going to follow them their whole life, and this half is going to not smoke, we'll follow them their whole life, and then compare the groups. They've never proven that smoking causes lung cancer. But the rate of lung cancer is so much higher, it's pretty much, you can conclude that that's the case. Yeah?
How would I know the number of dogs goes up with number of fire hydrants? Because that makes zero sense to me. That's like the...
It's a lot like the one we did. I did one in class a lot like it. That was the number of ministers, and it was something else. It was kind of number of liquor stores. That's the example that I gave you that was pretty close to that I think you could draw a generalization from.
With dog owners, or dogs equals dog owners, and therefore if you have more dogs, you have more dog owners, which means more population, which means
more fire hydrants.
If they don't have more fire hydrants, they could be in the towns.
No, the point is that these things will tend to go up together, and it's so the closest example that I gave you is I think that one is pretty obviously positive, and the closest example that I gave you was the one about ministers and liquor stores, which I think are not obviously related, and they're not related to each other other than it's the big city in the middle. So we're talking more about that kinds of stuff today. So today we're talking about some difficulties and disasters that happen inside of things with correlation. So when you have these regression lines, you can use them to predict different values of the y variable, right? You can say, okay, well, if your height is this, I'm going to predict your weight. Does that make sense? Now, if you used people in, I don't know, like Asia to make heights and tried to predict the height of somebody in Netherlands where they're really tall, that might not be a good thing to do because you're going too far beyond your observed range of x values. Another example could be like using temperature data to predict the temperature 100 years from now. That's like too far out of your data. Does that idea make sense? Okay, that's called extrapolation. Allowing outliers to overly influence the results. Sometimes one point can take your regression line and make it slope from negative to positive. Just 1 point. And the question you can ask yourself, well, is that 1 point just different enough I'm going to get rid of it and do the regression line without it there? You can combine groups inappropriately, and a really, really common thing for this to happen is with men and women. There's an example we're going to do today that says that, okay, well, if you are taller, you tend to drive faster. But that the relationship disappears when you separate men and women, because it just is the case that men drive faster than women. Men tend to be taller than women. So it's a variable, in the middle it's kind of like mucking stuff up.
What if it has to do with driving taller and gives you a better view of the road?
Well, maybe, okay, but that's not what it was. That's definitely not what's going on in the example that I'm going to show you.
Okay.
And then the other problem that can happen is if you try to use correlation to describe if you try to use a straight line relationship to describe something that's obviously curvy. So the point with this is you always should graph your data with a scatter plot first. You should always make a scatter plot of your data. If you have a lot of data, probably should use something like Excel or R, some other statistical software, and you should make sure that the points look like they're in a line-ish. Does that make sense? Ish, because they could be kind of like bunched around the line, but they're line-ish shaped. Okay. Just make sure you know some vocabulary. Extrapolation we kind of discussed a little bit. This is using the regression equation to predict stuff outside the data points. So using a regression equation to predict values outside the observed data. So if extrapolation means that, what do you think interpolation means? Inside the data. So these are y values that are estimated or predicted. For new values of x that are within the range of x's covered by the data set. Okay, so there's my pretend data set. So do we agree that as height goes up, weight tends to go up? Okay, so extrapolation would be like taking somebody who's way over here and trying to predict his weight from your line. That's outside of the x's that you observe. Does that make sense? Interpolation means you pick some x in the middle and predict that person's weight based on your regression line. It's like maybe you had somebody whose weight was 145 and 150, but nobody who's 147. But 147 is in between your 145 and 150, and you can predict that guy because he's in the middle. Yeah.
So extrapolation doesn't have to be something like absurd. Just
No.
Be something far
It's just
away from
outside.
your
Yeah,
data
and
set.
actually just outside.
Not even.
Not even really far away, just outside the data set. So it could be that you have data, suppose this was like now temperature and year, for example. You have data from the year 1900 to 2000. And you could predict 2015, well, that has already happened, 2017. Does that make sense? You could go like just, but going just a little bit outside isn't a bad thing. Going a lot outside is when things start to probably not work.
So it has to be still along the process. If it's an outlier, let's say, or like it's off, if it's really scattered.
Well, what you would be doing is you'd be saying, I have this regression line that I found, and I'm going to guess what this would be using the line itself. As in, this isn't a point that you know, it's when you're kind of guessing. Like, if I had a person that was 7 feet tall, how much would they weigh? As opposed to actually having one particular person who's an example. Yeah.
So the extrapolation is for when you're missing the x value, the interpolation is when they're missing the exact y value.
Nope. Extrapolation is when you plug in an x value that's outside the range of x values that you used. Interpolation is when you plug in an x value that's in between those two things. It's what x value you're plugging in. Does it fall within the x's that you had to make the thing or outside of it? Okay. It happens all the time. Extrapolation is bad, and this is an example. You guys seen the movie Wall-E? I haven't, but I know that there are fat people in it. So,
Should really
and
watch it.
I'll try again. An article in the Sacramento Bee noted that Americans are just too fat, and researchers say that 54% of all adults are heavier than is healthy. And if the trend continues, every single person is going to be overweight. All of us. I am doomed. This prediction is based on extrapolation, which assumes that the current rate of increase is going to continue indefinitely. Is that reasonable?
No.
No, it's not. Hopefully we'll do something about it. So no, I do not agree. Will not. And I think that the thing to say is that the rate of increase, as in like how quickly people are getting too fat, will probably slow or change. I'm actually pretty sure that the like childhood obesity rate, which was actually climbing, has actually stabilized / decreased some. So it's not like it's going to go forever. And actually, another example is that back in, oh God, what year was this? 2000, I think this was the year. There was a report saying that the national debt was going to be paid off. Because in that, right, we all laugh right now, right? Because in that year there was a surplus, and it looked like if that trend continued, it would be paid off. Did that happen? That's an example of extrapolation as well, right? The same as the idea that, okay, I'm going to assume oil prices are going to stay the same as they are now forever, right? It's also extrapolation, right? So you can see how it gets you in trouble, right? Okay, great. So here is a regression equation relating the putting distance in feet and the success rate for professional golfers. And this question was based on observations of distances ranging from 5 feet to 15 feet. So picking an x value between 5 and 15 to plug in for distance is interpolation. An x value outside of 5 to 15 is extrapolation, okay? We're going to use this equation to figure out what is the success rate at a distance of 2 feet and 20 feet. Okay, and your book does, I'm going to call it y again, so y hat is 76.5 minus 3.95x. So if I plug in 2, I've got 76.5 minus 3.95 times 2. Anybody get that? Here's some. I got 68.6. So if they're, according to this equation, if they are 2 feet away, they make about 69% of their putts. 2 feet's kind of close, isn't it? That seems like a low success rate for professional golfers if they're like this close to the hole.
Yeah.
That seems like it's kind of wrong. Okay, 20 feet. Y prime of 20. Or not prime, sorry, just calculus, ignore me. Sort of. 76.5 minus 3.95 times 20. Punch some buttons. See what you get. The number should make no sense, okay?
Negative 5.
-2.5. So when they're 20 feet away, they're all of a sudden like not, I don't know what this mean, right? Are they like not making putts? Are they like regressing backwards? Are they going, I don't know what that means, okay? Yeah, you can't have a -%, right? Yeah.
If they turn around and put -6 feet, it's 100% accuracy.
Yes, exactly. And so anyway, so obviously there's something going on here, right? Do you agree with that? And the problem is that the data used to make this equation range from 5 to 15 feet. These guys are outside of that, okay? And so the original data included values between 5 and 15, and at a distance of 2 feet, the actual observed success rate was 93%, which is quite good, right? Way better than predicted, right? And at 20 feet, it was 15.8%. So compare your results from part A to the observed success rates. These are actual numbers now. And why is it not a good idea to use a regression equation to predict the information too far beyond the range of values? So at 2 feet, what did we do? Did we underestimate success or did we overestimate success? We underestimate success. By a lot, right? If I said about 23%, does that seem like approximately? We had okay, so it's even worse. So 25%. And then at 20 feet, we had a negative success rate, which made no sense, right? So the point of that question is don't plug in numbers that are too far from the stuff you use to make your equation in the first place. Does that idea make sense? And what is too far depends on the context. In this thing, it was just 3 feet was too far, right? So. Okay. Give the values to a regression equation that relates student height and the father's height, and it was found using 10 female students. So the equation is y hat is 19.42 plus 0.658 times x. Give the value of the y-intercept. Does it have a meaningful interpretation in this situation? Explain. So what is the y-intercept? 19.42. Okay. So think about, back to like algebra 1, and you have this graph. It crosses there and has some kind of positive slope, right? When you're at the y-intercept of any linear graph, or any y-intercept, what is true about the x value? The x is equal to 0. That's always true, right? So to answer the question, does this have meaning? This means that when x equals 0, what does x stand for in this equation? Okay, I'll put that in parentheses for now. Father's height. Then y is equal to 19.42, and that's the daughter's height, right? Does that make any sense? No. Of course not, right? Whose father is 0 inches tall? Yeah, but no. Everybody had a father at some point in time. So there we go. So the answer is no. This would be a father with height 0. It makes no sense. Sometimes having things be 0 makes total sense. Like, 0 could be like if you had age and height, 0 could be like your height at birth, right? So sometimes 0 will make sense, but in lots of cases it won't, okay? So just ask yourself, if x is equal to 0, what does that mean in this context, and does that make sense or not? Okay, give the value of the slope and interpret what it means in this situation. So first of all, the slope is 0.658. And let's think about it as delta y over delta x. So y is student height. Do you guys agree? X is father's height. Yep. And I think it's easiest to think about these slopes as, number over 1. And say, if denominator does up by 1, what does numerator do? Does that make sense? So if father's height increases 1 inch, how much does a daughter's height increase?
0.658.
Yep. Daughter's height increases 0.658 inches. And we should add that's on average. Because it isn't as if that's the be-all end-all. Your dad's 1 taller than my dad, well, therefore, you are 0.658 inches taller than I am. That's obviously not always true, right? But on average, people that are taller tend to have tall dads tend to have tall daughters, usually. Okay. So use the equation to predict the height of a female student whose father is 70 inches tall. How do you do that? Plug in 70, and I think what you were saying to do is the same thing. 19.42 plus 0.658 times 70. I got 65.48 inches. Anybody else get that? Okay. Would it make sense that the daughters on average are a bit shorter than their dads? Yeah. Okay. Alrighty. So one student was 67 inches tall and her father was 70 inches tall. Find the residual for this student and explain what it tells you about his student, so this girl, in relation to the other female students whose fathers are 70 inches tall. So this is asking for the residual. Does that make sense? Okay. So we know that y hat, if we plugged in 70, was 65.48. That's from part C, right? And the residual is, now think about this, you want the residual to be positive if this person is higher than this average, and negative if they're lower. So this person is taller than the average, right? So for the result to be positive, we have to do this minus that, right? Which is y minus y hat. Or 67 minus 65.48, or 1.52. So this student is 1.52 inches taller than she should be, yes, than, because you must behave according to my equation, than other students whose dads are also 70 inches. And
Is
it's
that statement right? Is that statement right? And other students who dad, because that doesn't actually determine that their dads are going to be 70.
No, this part is definitely is, it is, yeah, it's a group, it's definitely talking about a group of people whose dads are all 70 inches tall, and in that subgroup she's 1.52 inches above their mean. Because she might not be, the same thing wouldn't be true if you're comparing her to people whose dads were taller or shorter. She's not 1.52 inches above average. She's 1.52 inches above average within people who have this criteria.
Yeah.
Does that make sense?
Yeah, I was just saying that that doesn't mean that all other dads and all of their daughters are exactly the same.
No.
This is worded kind of strange.
How about I add an on average?
When in doubt, on average.
When in doubt, on average. But that's what it's saying. This person is on average a bit taller, specifically that much, than other students whose dads were also that given height. Within that subgroup of dads with the same height, she's taller than the averages. Okay. So would it make sense to use this regression equation to predict the height of a male student whose father is 70 inches tall? No. No. Why not? And also, the equation was made using who? Yeah, made using women. So you don't generalize to men. This is actually a pretty big problem in medicine, I believe. I'm no expert, but I think a lot of drugs and procedures were tested on men, and they found that doesn't work super awesome for women all the time. Yeah, have you heard of that? That's the problem? Uh-huh. Like heart attacks too, right? Totally different symptoms in the different sexes, I think, or at least can be quite different. So this is not just this specific question, it happens in life as well. Okay, so these equations that I have here tell you what a man or woman's ideal weight is based on what their actual weight is. Like, so I think that if my actual weight is 175 pounds, I should weigh blah if I'm a woman or blah if I'm a man. It's just based on some survey results. I'm not saying it's actually true. It's a perception of what people thought. So predict the ideal weight for a man who weighs 140 pounds and for a woman who weighs 140 pounds, and we're going to compare the results. So for the woman, yeah, we're going to predict her ideal weight if she actually weighs 140. Does that make sense? Okay. So 44 plus 0.6 times 140. I got 128. Did you also get that? So for the man's ideal, if it's 53 plus 0.7 times 140 is, I got 151. Okay. Does this kind of stem with what you think most men and women that weighed 140 pounds would say about themselves? Wait, you don't think so? Okay, well, I think it does. So this says, so let me explain. This says, if I weigh 140 pounds, I really would like to weigh 128 as a girl. Okay, on average, that's what people say, not like you particularly. And if you're a guy, you want to weigh more.
But what if she's 6 feet tall and really, really buff? Like, it doesn't put much into account.
I think the idea is that women typically want to weigh less than they do, and men usually want to weigh more.
That is exactly the ideal, is saying that women typically, on average, not every single person, on average, you have to remember that. This is not like exactly for every single person. On average, women want to weigh less, and in this case, men want to weigh more. Up to a certain, that's all it's saying.
And remember, this was 2010 probably, so things have changed.
Things have changed. So I think if a woman weighs 140 pounds, on average, she wants to weigh less. I mean, that person you're describing who's 6 feet tall and weighs 140 might have an eating disorder and think they should weigh less than they do. I mean, like, it does actually happen.
Yeah, so it's not actually like what an optimal healthy weight.
I didn't say it's not a healthy weight. This was done from a survey where people were asked what their weight was and what their ideal weight was. It's not like a doctor saying this is your weight, this is your ideal weight. It was a perception of what people wanted. Yep. And if a man weighs 140, he wants to, I was jealous of him then. He wants to weigh more. On average, yep.
I didn't know I never thought anyone wanted to weigh more.
Yeah.
140 is pretty skinny for a guy, right? I mean, and so they might want to be more buff. So,
Yeah, that weight for me for a woman, that's about my weight now, and so I'm perfectly okay with that weight.
but the point is that it's an average across a lot of people, and in general, like we said, a lot of women want to weigh less, and sometimes men want to be more fit, more muscular, which implies weighing more. So it's just an average across a large swath of people, not like your personal opinion.
So when it says compare results, do you always need to write the woman, you can't just write women want to weigh less, men want to weigh more?
Say when they weigh 140 pounds as well. Like specify that as well, because I haven't tested, but it might be different if we hit like 200.
Yeah.
Like if we hit 200, the men's equation might flip and they might want to weigh less all of a sudden. Like I just haven't plugged in 200 to check and see, but I can imagine that being true. And we specifically observe a relationship for 140. Does that make sense? Yeah.
Because if you plug in
Yeah.
110 for the woman's ideal, she weighs exactly what she wants to weigh.
Which, yeah, so it does stuff like that.
Yeah, with the 200, so you would have to have like a minimum and a maximum.
Nope, it's just that the conclusion you're going to get in your comparison depended on the fact that you plug in 140. Does that make sense?
The conclusion's
So
gonna
the
be based off the
conclusion
information
is
provided.
based on what you get in this step, and what you get in this step depends on the fact that was 140, so you cannot say like, women always want to weigh less and men always want to weigh more. That's not true, right? But you can say when these two people weigh 140, then this is true. Does that make sense? Okay, good. Great questions. Woo. Okay. Do the intercepts have a logical explanation, interpretation in this context? No. So this means the actual equals 0. Does that make sense? Like this first equation, its y-intercept is 44, right? The second equation, its intercept is 53, right? In both cases, that means the x variable is 0, right? If your actual weight is 0, you really want to weigh 44 pounds.
So anytime we're dealing with height and weight, we just put no for that question.
Well, I mean, I think you should explain what it is, okay? Like say, like, this means this would predict the actual, this means the actual weight is 0. Is 0, which makes no sense. Like, that's enough. But tell me that you understand that the x variable is 0, and that's why it has no meaning. Does that also make sense? That's what it means to be on the y-intercept. Your x is 0, and if that means the actual weight is 0, that makes 0 sense. Doesn't mean you're like in vitro and want to weigh 53 pounds. I'm pretty sure that newly conceived babies don't want to weigh 53 pounds. So, do these slopes have a logical meaning? And let's interpret one of them and see, okay? Let's look at the lady slope. M equals 0.6. What are the units of the y? Y's the
Ideal weight.
ideal weight. What's the x? Actual weight. Okay. So if actual weight increases by 1, ideal weight increases how much? By 0.6. I don't think I see any obvious problem with that, do you? No. So you could say yes, and then you could say, for example. I didn't ask you to interpret both, so you only have to, give me something that tells me you can interpret one of them. Because is the men's one going to be any different in any essence? It's going to be if it's going to be like 0.7 instead, right? Okay. Yes?
Why do you always use 0.6 instead of just 0.6?
I'm afraid I'm going to lose the decimal place. It's just my personal preference. I just like using 0.6, but I'm not going to dock you if you don't.
It's just easier to read.
I think it's easier to read, and it's in my book. I think I was told in school that I had to put the 0 there, and I can't undo the thing I was taught when I was 8. That's my suspicion. Your book doesn't even do it all the time either, but I fix it because I like it better when it's 0 point something. Okay, so I think I mentioned that sometimes there are influential outliers that can drastically change your line. So in this picture, we have earthquakes that occurred in the continental US, and these are all the earthquakes that were a magnitude of 7.0 and at which there were at least 20 fatalities. And it's the correlation between deaths and magnitude is just 0.26. But do you see that there is one point that's kind of appears to be worse than all the others? You see that? He's way off the chart, right? And that slope has a positive, that line has a positive slope, right? That's if you
Even though it looks like it should be negative, that line wasn't there.
Exactly. So if this dot is removed, this is what happens. And it's definitely not intuitive. It looks like big earthquakes have fewer fatalities. That seems like that might not make sense, but if you throw at that one point, it's definitely true, right? So that one outlier greatly affected thing, and the thing is do earthquakes always happen where there's a lot of people? I think that probably skews this data quite a bit. So there's one earthquake that happened to occur in a big city and happened to also be a large magnitude.
In 1906.
Also pre-good buildings,
Yeah.
right? So this thing could be confounded by all sorts of problems. It could be the case that there's large variability when the earthquakes occurred in terms of time and technology's advanced a lot. So some problems could be that maybe technology plays a role. Maybe population. Like if they included Alaska in here, it'd really mess stuff up because lots of earthquakes happen in Alaska and not very populous places, right? Also just observe what happened to the correlation coefficient. So which one is stronger? Is 0.26 stronger or is negative 0.824 stronger? The negative 0.824, remember this is closer to plus or minus 1. That's when it's stronger. It means those points are closer to the line. So the correlation got better with that one data, a lot better with that one data point thrown out. So just FYI, that could happen. So that's the outliers. The other thing is inappropriately combining groups. So this is a height and lead feet. For a sample of college students, a scatter plot of their height and what is the fastest you have ever driven a car is shown below. In the original scatter plot, there's a modest correlation coefficient of 0.39, which isn't spectacular, but you can see that it kind of like tends to go up together, right? Ish. So this suggests that these two variables are at least a little bit associated. But if you separate out men from women, this disappears completely. And here's the picture. Oh, there was the picture.
That's all right, we have it.
You have it on your paper. So let me see if I got smart at it. Okay. Do you see that the picture on the left, what's the correlation coefficient there? Which is very nearly 0, isn't it? And the next one is negative point, which is also effectively 0. So the correlation disappears. So the overall problem here is you should separate obvious subgroups. There's another context in which that happened. There was a case at a university, I think, where women were claiming that they're being paid less than men. But the problem was that the men had been at the institution longer than the women on average, and so that meant their salaries were higher, and it wasn't really the men versus women thing, it was the length of time they're at the university. So, point is, it can happen. Okay, so it's important to look at a scatter plot before you calculate a regression line. And when the data is curvilinear, or has some curve pattern, predictions based on a straight line are likely to be inaccurate, meaning not. So here's an example of that. This is from your textbook. So this is a graph of the population of the U.S. for each census year between 1790 and 2000. And I want you to look at the difference between the curved line and straight line predictions for both interpolation and extrapolation. So the dots are the actual measured populations. Have you guys seen exponential growth before in a previous class? This looks like pretty obviously like one of those exponential growth things, right? As in not a straight line, right? If you tell statistical software to do a straight line of best fit using that least squares thing, you get out this dotted line here, okay? So do you see how it's kind of like not good for anything?
No.
Do you see what I mean? Like it
Matches like 2 points.
Yeah, it's not, and it's also not spectacular in the middle either, right? But it's really, really bad the farther away you get, right? Specifically, the exponential thing increases a lot faster than the line does. So that's the problem. So what did I write here? The moral of this story is only use a straight line if your points fall in a straight line. Yeah, it's kind of weird. I don't know. That might be like my scan being wrong, or something like that. Because like I had to scan a book and pages might have gotten warped. But I actually, after drawing the line in, it looks like it's okay. So like if I were to extend that dotted line,
Well, I mean, in regards to the y-axis, it doesn't look right.
what do you mean y-axis?
Because if you look at where 250 is, it looks like it's below the 250 mark.
No, my paper looks like it's above it.
It might just be from where I'm sitting, but.
Okay, so we'll just say the people that made this don't. They kind of suck. It says 269. That's above 250.
Doing the most.
What was that? Why is that a problem?
I don't know.
But basically, the other moral of the story is that they need like grid lines that go all the way across, right? Yeah, I think it's fine. Okay, and I think they're doing an estimate for like 2030. They're saying this is the straight line estimate, that's the curved estimate, which one looks like it's actually going to hit the actual pattern, and it's the top one. Okay. And so I brought this up already, but plot roughly what happens to temperature here in Fairbanks over the course of a year. So if we start our year in, we'll call January 0, 1, 2, 3, 4, 5, there's May, June, July, August, September, October, November, December. Did I put an extra one in there? Crap. Renumber. Reletter. January. February. I missed a month. What's after February, guys? Come on, help me out. April, here we go.
May, June, July.
April.
March comes before April.
Your math teacher's ashamed of herself. March, April, May, June, July, August, September, October. Okay. Whew. Whatever, call it good enough. We could also have numbered them, but I can't keep track of what numbers they are. So in January, it's usually below 0, right? And then it starts to go up-ish. It goes up. When does it peak?
Like heat-wise?
Heat-wise, June, July-ish, right? And then by August, it starts to get depressing again. And then it starts to go down, and December's kind of like, the same, right? If I plotted lots of years, there'd be some years that were colder and warmer, right? It'd be like a little bit of variability there, but yeah, like last winter, I think we did not see minus 40 at all, did we?
Negative 23 was.
It's ridiculous. Okay, sorry. Okay, so would using a straight line make any sense? No.
It's a rainbow.
It's a rainbow. If you tried to use a straight line, what would happen is you'd basically get that. You get like a horizontal line, and it would say that the correlation coefficient was like 0. But there is a predictive relationship, it's just not a straight line relationship, that's all. Okay. And the last thing we want to talk about is that correlation does not prove causation. So, for example, do you think that the sales for weekly flu medicine will increase along with coat sales?
Yes.
Yes, both will probably increase together, even though these variables have very little to do with one another. You don't get a cold and then go buy a coat, do you? Or you don't go.
People prep for it.
Yeah, but
They don't get cold.
so what tends to happen to us at the same time when flus hit us and coat sales go up? Tends to get cold. Yeah. So winter happens. So winter causes us to go inside more, which causes us to get more germs, right? And winter causes us to buy coats, right? That's called a confounding variable. So the point is that it's not like one thing causes the other. But, so I think, what did I say here? That buying a coat doesn't cause you to get the flu, right? Or vice versa, right? It's winter that's a problem.
Winter is the confounding.
Winter is a confounding variable. This next one is one that you wouldn't obviously expect, but this has definitely been observed in science. People who use vitamin supplements get fewer colds than people who don't, and often this has been taken to mean that vitamin supplements mean you don't get colds. Now, that's actually not always the case, I think. There's something that happens a lot in health studies called the healthy user bias. Have you guys ever heard of that? HELT. It's okay if you haven't. I hadn't either if I read a book.
Were you saying I'm taking multivitamins every day for nothing?
Maybe.
People who take vitamins generally take better care of themselves.
That's the exact thing. People who take vitamins tend to take better care of themselves.
Or there's people who don't eat well, so they take the vitamins to equal it out.
I don't think it works that way. Yeah, I think that this is kind of what this is saying. The point is unless you, I can't multitask, I have to finish writing, take better care of themselves. It isn't an outlier as much as that really is also a confounding variable. Taking care of yourself is kind of like messing with your results a little bit.
How dare you?
How dare you? So in order to actually determine, is it the case that vitamins are causing the better health, it'll take you and put you in two groups and say, this group is going to take a vitamin, this one's taking a placebo, and we're going to see if you are actually healthier if you're in this group. And unless they've done that, they can't say for sure. And there have been instances, like this next one, so I think it was back in the 90s, but I didn't Google it, so don't hold me to this, okay? There was a survey done on a lot of nurses, and at that time, it was found, at this time the survey was done, it was found that taking estrogen drastically decreased the rate of breast cancer. And so people said that, so without doing a study, they went and recommended taking estrogen for everybody. And then they went and did an actual study where they put women in two groups and they said, you take estrogen, you do not, we're going to compare your cancer rates. And cancer, I think, went up in the estrogen group. Have you guys heard of this, any of you? Yeah. So that was an example of the healthy user bias. Does that make sense? So be aware of stuff like that when you read things in the newspaper. There was a study about bacon recently, and I love my bacon, so I'm a little biased here. But it said that if you eat bacon, you get cancer at a higher rate. But people that tend to eat bacon, on average, don't take great care of themselves because they drink lots of soda and also smoke, so that's confounding the stuff in the middle. So I'm going to keep eating my bacon as long as I run. Yeah. It's also self-reporting, which has a lot of its other problems. Like when you report what you ate, I don't remember what I ate last month, let alone like 2 days ago, let alone like for the last year of my life.
Feeling guilty. Yeah, I didn't eat that.
Yeah, I didn't eat that bacon. Okay, so there we go.
So wait, what about those like advertisements where it's like you have a toddler who's not eating enough food, so they tell you to give them a dietary supplement?
I don't know enough about this to have an opinion, and I also don't have TV that gets commercials. I just watch Netflix. So, yeah. Anyway, so moving on. So if you want to establish some kind of causal relationship, the thing you must do is you must collect data using what's called a randomized experiment. And we'll talk more about those in like a later chapter. But the basic property is that you divide people into groups and quote unquote treat one group and don't treat the other. I'm sure you've all heard of this for like drug trials, right?
Control group.
There's a control group and they often get a sugar pill. And sometimes they do things they don't tell the doctors who has which pills, stuff like that. I mean, so we'll talk about what all those things are in a later chapter. But you take people, divide them into groups, and you say randomly, you're going to get this, you're going to get this, and you know,
Or they don't tell you what you get.
Yep, exactly. You take blue, you take red, and that's it.
A lot of the times, the doctors don't even know which group.
And a lot of times the doctors don't even know which group they're doing, yeah. They've also, it's kind of cool, they've done this with surgery. So I can't remember what it was for, but I think it was meniscus surgery on your knee. There was a study done, and they gave one group surgery and one group fake surgery. So they said like it's not invasive. It's like I think it's sort of like one of those microscopic ones where they like go into your knee and it's not really. So they made them both go in. They gave them like all the same anesthesia, but on some people they gave them fake cuts, and they didn't actually do the surgery, and they found that the surgery did nothing to help anybody.
Until they tried to rotate on that knee.
No, like look it up, okay? Like this definitely was the case that often the surgery wasn't actually a solution. It's crazy, okay? The things they did to keep the groups even was pretty amazing. Yeah.
Was it because of the physical therapy?
I'm not. I don't know enough about it to say. I'm just not sure, but I do know that they did this like. They can do this with things like surgery, which is kind of crazy. I'll look it up. Okay, I'll look it up and I'll tell you more later. Okay.
People didn't have to pay hospital bills.
I'm pretty sure they got this for free. I'm sure that there was something like that. Yeah. Yeah. We're gonna make you our guinea pigs, and then we're going to
Placebo effect
charge
is
you.
quite
Yeah.
amazing.
When they did this, these probably, I'm just trying to think of like the risk benefits of doing it. Did they actually explain the full risk benefits?
I'm sure that they did. I'm sure they have to do that. There's all these ethics requirements. You have to do these things. There are procedures. I don't know them because I'm a mathematician, not an actual science. I guess that. So if you want to know about it, I would suggest we should just Google it. Like look it up. Okay, I'm sure you could look up about like knee surgery statistical study, and we'll find something about it. I'll look it up myself. I just haven't had time. Okay. I changed my notes and failed to change my slides, so I'm going to add in a slide. You ready? The next thing Yort says is there are at least 4 possible interpretations of an observed association between the explanatory variable and the response variable, right? So explanation number 1 is that there is causation. So the explanatory variable is causing a change in the response. This can only be concluded if you do a randomized experiment, not a survey. And if you start to read stuff online, you're going to realize, holy crap, lots of recommendations are based on surveys. Why am I listening to you? Because you shouldn't do that. Bad statistics.
So when it starts out saying a survey was done, should we stop reading?
No, you should, because surveys give you clues as to what kind of randomized experiments should be conducted, right? They give you hints at where to look. They're useful for that, but you should not use them to make conclusions that are hard and sound. Does that make sense? Okay. Item 2, there may be causation, but confounding factors make the causation difficult to prove. So a confounding variable is a variable that is not the main concern, but may be partially responsible for the results. For example, this is my example. Does lack of exercise lead to weight gain? Yeah. And the confounding variables are other factors that could be affecting that.
Like diet.
Yeah.
Diet.
All those Doritos you're eating.
Well, common workout, daily workout, like I walk to class a lot and
Yeah.
that's still not considered workout.
Well, I think it is actually.
It is.
But the confounding thing are other things that could be leading to that, like diet matters. I think also stress level matters a lot.
I think gender.
Yeah, gender probably also is affecting this.
Isn't there like heritage factors?
Yeah, there's probably also some genetics. Sure. Yep, sleep definitely matters, which probably is also. So the point is that there are lots of other things that could be causing this, and it's not just exercise. Okay, that's the point. Okay. Item 3 is that there is no causation. The observed association can be explained by how one or more other variables affect the explanatory and response. For example, and you're going to hate this example again, but it was the whole dogs plus fire hydrants. And they could both be explained by city size. Yep, city size, populations.
So that's the causation.
Yeah, probably. Well, it's not really causation. Like, big cities don't cause dogs to exist, right? But that's what's kind of making it happen. They attract those people. And
That's not confounding because it doesn't directly contribute. But
confounding, from my definition and from what if I'm interpreting correctly, is that confounding are partially responsible, like additional things,
Right.
whereas this one is it explains it away.
Sure.
Does that make
It
sense?
could just be it could be like a
Yeah, it's like
outlying reason more.
like an underlying reason, I think would be what you call that. And the fourth thing is that the response variable is causing a change in the explanatory. It's not obvious which is causing which. Like there was an example that I think you, can't remember if you read in your book, because I assigned some problems, but did I give you one about church attendance and health? Yeah, there was one about regular church attendance.
Yeah.
So regular church attendance, and the people wanted to include that regular church attend, ANCE, implied health? Or is it the case that health implies regular church attendance? It's not clear which way that's going to go. Does that make sense? Because it could be the case that you go to church because you can, right? If you're super unhealthy, you can't get out of your house and go to church. So it is not clear in that group as if it's if which way the direction goes. That's kind of the point.
And that's called a chance.
What that is saying I made it's supposed to be a change. I boo-booed. Spell check doesn't catch that. So the response variable is causing a change in the explanatory variable. I missed a G and not a C. Thank you for pointing that out. The point is that the association might go the opposite way of what you wanted. There's various stuff about health that I've read that people think that being lazy contributes to obesity, but maybe being obese causes you to be lazy, as in there are hormones that then make it harder for you to get up. And so it is also in ways you wouldn't expect that also I think happens. Okay. So this is a scatter plot. So this has the average number of persons per household in the U.S. for census years between 1850 and 2000. I probably got this from the companion website, and I made the scatter plot using Excel. Okay. If you can get Excel to label your scatter plots, great. If you can't, you should label your axes by hand. Does that make sense? So in this case, this lower axis is year, right? And this one is number of persons per household. And that is an average, so because we're going to average bunches of whole numbers, we're probably going to get a decimal. Doesn't mean we actually have half a person, okay? It's just an average. So does this relationship appear to be linear or curvilinear, more or less? Is it positive or negative? So negative for sure, that much is pretty obvious. And I would say, it's almost never going to be perfect, but does a straight line seem like it could go through a lot of the points? Yeah, so I would say that is probably linear. And the negative means that as the year increases, number per house decreases. And a big thing happened between 1850 and now. Birth control, right? So on average, people do tend to have smaller families now.
Plus, it's just not as popular to live with your whole generations and generations.
Yeah. Oh, and you're right. It could be the case that we have had multi-generational households that run multi-generational here. And then the last question says, on your scatter plot, add a line that you believe fits that pattern. So draw in the thing that you think kind of goes the best along. This really is just a guesstimate. And use it to estimate the people per house in 2010.
1.8.
I think it's above 2.
2.2.
Yeah, 2.1.
Sorry.
That's okay, yep.
Small on ours.
So about 2.1, 2.2 people, approximately. What you would get would depend on what your line would look at, and as long as you're within a certain margin of error, you're okay.